Hi everyone, I'm Sujin, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to see a very important experiment in physics laboratory, that is how to determine the energy gap in a given semiconductor. So let us see the brief outline of the experiment, how we are going to go about this experiment. The first thing is the aim of the experiment. Aim is a statement that clearly describes the purpose for what we are doing the experiment. If you look at the aim, it should be very clear of why we are doing the experiment. Then apparatus required. We may call it as the tools or the components or the equipment that is required to do the experiment. Then comes the theory. So whenever you do an experiment, it is very much required to understand the theory or the mathematical background behind the experiment. Okay, unless you understand the theory clearly, you will not be able to perform the experiment. And it is always vice versa. If you understand the theory well, you can do the experiment well. And when you do the experiment, you will clearly understand the concept behind that experiment. So it is very important that you are prepared well with the theory before you perform the experiment. So what we say here is there is always a very good correlation between theory and experiment. So many times whatever the scientists do, they predict they have some assumptions or they have an hypothesis. Unless they do an experiment and verify the results with the theoretical values, that theory will not be confirmed. So we'll be using the same approach here even in the laboratory because it's a learning stage for you. And then comes the circuit diagram. Circuit diagram, we say whenever we need to do an experiment where it involves a flow of current. So you need different components, the connecting wires and a circuit. So if you have the circuit diagram and you are clear with all the components in the circuit diagram, you will be able to connect them very easily and perform the experiment. And if it is not a circuit diagram experiment, you may have an experimental setup. Again, in an experimental setup, you have different components and all of them have to be arranged in a systematic order, in the order that is mentioned. So you need to first understand how to set up the experiment. Then comes the procedure. Procedure is nothing but a plan of how to do the experiment. You should have a plan how you're going to do the experiment, and it consists of a stepwise procedure. Step 1, what you're going to do, step 2, step 3. So even before you start the experiment, you should be well aware of all the steps you're going to follow while doing the experiment, and that we call it as the procedure. And then comes the observation table. Observation table is nothing but a table or a tabular column which is drawn to note down the readings. When you do the experiments, whatever observations you note down, you will have to record them. So you put them in a systematic manner in an observation table so that it becomes easy for you for doing the calculations. Then comes the calculations. In calculations, as I have explained, whatever you study in the theory and you have a mathematical formula for it, the observations that you have noted down, you will be putting it in the formula and you will calculate the readings and try to see whether they are matching with the theoretical values or not. Then comes the model graph. Because in some experiments, you will analyze the data. The data you have collected while doing the experiment has to be analyzed using graph. So before you do the experiment, you also need to have an idea of the graph. What is it you are going to take along the x-axis, what it is along the y-axis, what will be the correlation between the two, whether the readings are following the trend that you expect them to go about or not. And then comes the result. Result here, when we say, when you are doing the experiment, you will be taking a number of readings, different trials you take, and to minimize the error, you will be always taking the average of all the readings. So the result comprises the end value, what you are getting after doing the experiment. Then comes the viva voce. So viva voce is nothing but an oral examination where you will have to answer some questions. It consists of a set of oral questions which are intended to test your skills as well as the knowledge. So you should be able to communicate what you have done in the experiment and whatever results you are getting based on the theoretical background you have. So this viva voce will have a set of oral questions where they'll be asking you about your theoretical knowledge, to test your theoretical knowledge as well as your practical skills, and you should be able to communicate it very well. So this is the brief outline we are going to follow while discussing the experiment. Now, let us understand the aim of this experiment. The aim is to determine the energy band gap of a given semiconductor diode by studying the variation of reverse saturation current at different temperatures. So the important terms here is you are going to determine the energy band gap. Energy band gap of what? A given semiconductor diode. So how we are going to do it is by studying the variation of reverse saturation current at different temperatures. So whatever diode we'll have to find the energy gap, we will be subjecting it to variation in temperature. So at different temperatures, how the reverse saturation current is going to vary, we will note down and we will find the energy gap of a semiconductor diode. Now let us understand what a band gap is. A band gap, also called an energy gap, is an energy range in a solid where no electronic states exist. Means in that particular gap, you will not find any electronic states. So otherwise, in other words, we can put it as the gap between the highest level of the valence band and the lowest level of the conduction band. So let me explain this to you very clearly. You can see the diagram here. In the diagram, we are showing it space coordinate versus electron energy, and this band here represents the valence band and this is the conduction band. First, let us understand what a valence band is. Now, let us go back to the structure of atom. So, whenever we talk about an atom has a nucleus at the center. Of course, it is positively charged and you have electrons revolving round the nucleus. So, this is the first orbit. I say there are electrons here and more number of orbits. As you keep on adding the orbits, there are more and more electrons. Depending upon the electrons, you have the number of orbits. So, let us consider, say, 8 electrons in the second, 2 electrons in the first, maybe 4 you take in the third orbit. Now, this is the nucleus which is positively charged and these are the electrons which are revolving round the nucleus in fixed orbits. Now, these electrons which are in the outermost orbit, we call them as valence electrons. So what are valence electrons? The electrons that are present in the outermost orbit, we call them as valence electrons. Now, I'm talking about a single atom. When I take a solid, okay, so we are taking a semiconductor. A semiconductor is a solid. It consists of n number of atoms, capital N. If I say it may be an Avogadro number of atoms, 10 to the power of 23 atoms. So each atom may have the same structure as this we have seen here. So now all the n atoms will have valence electrons. And if we denote the energy of these electrons like this by energy levels, there are n number of atoms and in each there are different number of valence electrons, and the energies of all the valence electrons put together form a band. If they are very closely spaced here, I can imagine that it is like a band, which we are calling it as the valence band. You can see here. So you need to understand what a valence band is. Valence band here represents the energies of all the valence electrons put together, which form a, because they are very closely spaced, they form a band, and we are calling it as the valence band. Then you have the conduction band. What is conduction band? The range of energies possessed by the conduction electrons, or conduction electrons are nothing but free electrons. Conduction electrons, because only those electrons which are free can conduct. So that is why we call them as free electrons or conduction electrons. And the energies of all those free electrons form a band, just the way we have seen here, and it is called as conduction band. Now, also let us understand how these electrons can be made free. So, I told you this is the nucleus which is positively charged, and these are the electrons revolving round the nucleus, and there is always a force of attraction between the positively charged nucleus and the negatively charged electrons, which we call it as the electrostatic force of attraction. So these electrons are bound to the nucleus. Now, if we have to remove these electrons, we need to supply energy to these electrons so that they can overcome this force of attraction and become free. So when we supply an energy, if these electrons come out, they become free. Only when they become free, they start conducting. We call them as conducting electrons. And the energies of all those electrons put together form the conduction band. So now this diagram should be very clear for you. In valence band, we represent the energies of all the valence electrons. And in conduction band, it represents the energies of all the conduction electrons or the free electrons. Now, the gap, what we are seeing here, it is the gap between the highest level of the valence band. This is the valence band and this is the highest level. What we are showing here, EV here represents the highest level in the valence band. If I imagine a number of energy levels like this, so this will be the highest level in the valence band. And now if I say this is the conduction band, here also there are energy levels like this, a series of levels placed very close together, and this will become the lowest level in the conduction band, which we are representing by EC. So now the gap between the lowest level in the conduction band and the highest level in the valence band, we are calling it as energy gap or energy band gap. So what is band gap? Because we are going to determine the band gap or the energy band gap in a given semiconductor. So you need to clearly understand what it is. So it is the gap between the highest level of the valence band and the lowest level of the conduction band. Sometimes we also call it as forbidden band or forbidden energy gap. Why we are calling it as forbidden band? Because there are no electronic states in this region or in this area. So we call it as a forbidden band. So in a given semiconductor, we are going to see or calculate this energy gap. Now, why we are calculating, what is the importance of this band gap? If you understand, then the experiment will be very clear for you. Band gap is a major factor in determining the electrical conductivity of a solid. So whenever you take a solid, okay, if you see in materials, they can be classified as some which are conducting, means which conduct or which allow the current to pass through them very easily. You call them as conductors or good conductors. In conductors, the electrical conductivity is very high. When you want current to flow in a circuit, so you need to use a conductor so that the current can flow through it. Now, when you do not want the current to flow through it, you need a bad conductor. They are also known as insulators. So, if you know the electrical conductivity of a solid, it can be utilized appropriately for the intended use. So, it is very important to know the electrical conductivity of a solid, whether its conductivity is high or is it low, or it does not conduct at all. So, in order to know the electrical conductivity, we need to know the band gap. Okay, how we are classifying them? Substances with large band gaps are called as insulators. So, if the band gap, that is the gap between the highest level of the valence band and the lowest level of the conduction band is very large, then we call them as insulators. And those with the smaller band gaps, if the band gap is very small, then you call them as semiconductors. And in conductors, the valence and the conduction bands overlap. Okay, we will try to understand these with the help of energy band diagrams. So now this classification we will try to understand with the help of energy band diagrams. These are called energy band diagrams. Where we are representing the energy bands. So how we are seeing here is the valence band. This is the valence band. I have clearly explained the range of energies possessed by the valence electrons. We are denoting by valence band. This is the conduction band. The range of energies possessed by the conduction electrons. Now, if you see in insulators, this band gap is very large. It is of the order of 8 to 10 electron volts, almost 8 to 10 electron volt. The band gap in an insulator will be depending upon the material or the insulating material you are taking. The band gap is huge. So, when the band gap is big, then you will classify them as insulators. Why it is, we will understand in the experiment. Now, coming to semiconductors. Semiconductors, if I say, they are partial conductors. Their conductivity lies in between conductors and insulators. So here if you see, the band gap, if you see here, is very small when compared to the insulator. So it is usually of the order of 1 electron volt. If you take the two famous semiconductors, that is silicon and germanium. For silicon, it is around 1.1 electron volt, and for germanium, it is around 0.7 electron volt. So, this band gap for semiconductors is of the order of 1 electron volt. Now, coming to conductors, the valence band and the conduction band, they overlap with each other. If you can see in this region, there is no gap. Almost there is an overlap. The conduction band and the valence band are overlapping with each other. Okay. So, what does this energy band diagram explain? So, what it tells is, because the valence band and the conduction band are overlapping with each other and there is no gap in between the two, the valence electrons can easily jump into the conduction band. They can easily go to the conduction band, or in other words, I can say they can be made free very easily. So when they are in the conduction band, they start conducting. So they are good conductors. So that is why we are calling them as conductors, because the gap is very small. The transition from valence to conduction band is very easy. So they are conductors. Now coming to semiconductors, the gap is around 1 electron volt, I said. So those valence electrons, when we supply an energy of around 1 electron volt or above that, depending upon the material, they can go to the conduction band and then they start conducting. Okay. Now you need to supply very little energy, I can say, of the order of 1 electron volt. Then they become free, they start conducting and they behave like conductors. Otherwise, they do not conduct. Now, when you come to insulators, since the band gap is very small, you need to supply so much energy for them to go from the valence band to the conduction band. So they are insulators. They do not conduct. Okay. In nature, we find materials which are insulators. Some are insulators, some are semiconductors, and some are conductors. So depending upon our requirement, in some cases we need conductors where they need, suppose you have to allow the current to flow through them or heat to flow through them. You need good conductors which can carry the current very easily. So you will use conducting materials. In some cases, you do not want to allow the current to flow through them. You want to insulate. No, suppose you have a wire which is carrying current. So to carry the current, you need a good conductor. So we use copper wires. Copper is a good conductor, but that wire cannot be exposed. So you need to insulate it. So we use some plastic or rubber. So to insulate, which is an insulator. So we have, in certain cases, we need insulators, and in certain cases, we need conductors. So depending upon the requirement, we choose the material, and how we are classifying them is based on the energy gap. So that is why I said this is very important to understand the energy gap. Now coming to the apparatus required. So the first one is the semiconductor diode. The semiconductor diode whose energy gap we are finding out. So I have shown the semiconductor here. Generally, a semiconductor looks like this. Okay. How do you identify? It is a anode and a cathode which are represented through the symbol. So when you see here, what is the positive side? This is the positive, and where you see this line, this is generally representing the negative. And when you connect it in a circuit, it is always represented by a symbol. This is a symbol which is used to represent a semiconductor diode. This is the positive side and this is the negative side. So this is the symbol which is used to represent a semiconductor diode. Now, if you see in the experiment, the semiconductor is placed here. It is not visible clearly. So I have shown it here, okay, for a clear view. So you know how a semiconductor looks like. And now this semiconductor is placed in a vessel, because we have seen that we are going to vary, we are going to heat it, and at different temperatures we are going to note down the current. So you need a power supply, a microammeter, thermometer, and a heating arrangement. So at your level, since it may be difficult, you are still at the learning stage, most of the times we use trainer kits. So this is a trainer kit. Trainer kit to determine the energy gap. So it consists of almost all the required components. So you have a fixed power supply. If you see here, a power supply which is inbuilt. So this is the positive terminal and this is the negative terminal. So you can see the fixed power supply, and then you have a microammeter. So ammeter, what is an ammeter? An ammeter is an instrument which is used to measure the current. Here, since the current that is flowing through the circuit is very small, we use a microammeter. You need to know the relationship between microampere and ampere. 1 microampere is equal to 10 power minus 6 ampere. So this is very small. So whenever you need to measure small currents, you use microammeter. You also have a milliammeter. So milliammeter means 1 milliampere is equal to 10 power minus 3 ampere. Okay, so we are using a microammeter. You can see this in the kit here, and these are the two terminals. How this is inbuilt, and here you have the positive terminal to connect to the ammeter, microammeter, and this is the negative terminal. And now you also need a thermometer, because when you have to heat it, so this is the thermometer which is used to measure the temperature. And then coming to the heating arrangement, because we have to heat this semiconductor diode. We cannot just take it like that and heat it. So we use an arrangement. What is the arrangement we are going to use here is, you will take this semiconductor diode and keep it immersed in an oil bath. What is oil bath? Generally you take oil, okay, in a container. Here we are taking a copper vessel, and in that copper vessel, maybe till 3/4 we will be filling it with oil. And when you heat the oil, this semiconductor which is kept immersed in the oil bath also gets heated up. And you need to understand why we are using only oil and why not water or some other material. Because an oil bath is generally used to get uniform temperature. The temperature throughout will be uniform. And also in some cases where you need very high temperatures, very high in the sense more than the boiling point of water. We know that the boiling point of water is 100 degrees Celsius. So if I take water and start heating it, I can go to a temperature of around 100 degrees Celsius. But if I have to heat a material to a temperature more than 100 degrees Celsius, then I use maybe oil whose boiling point is very high. That is the reason why we use oil bath. So here also we are going to use oil. We are taking oil in this container, which is a copper container. Copper, which is a very good conductor again. And we will keep this semiconductor immersed in the oil. Okay. And then you can see the connections here. The positive of the semiconductor is connected here and the negative is connected here. Okay. And the entire thing is kept inside a wooden box. This is the wooden box, and later on we are going to keep a lid above it. So why we are using this wooden box? Wood here is an insulator, no, which prevents the loss of heat. When I am heating this oil, the heat should not be taken away into the surroundings. So that is why we keep it in a wooden container, which is a very good insulator. And also sometimes this region in between also we will fill it with some cotton or wool, which is again an insulator. So this is the entire arrangement, which is the heating arrangement. Heating arrangement means you are taking a vessel in which you are taking oil. You are keeping the semiconductor immersed in the oil and giving the connections, positive connected here, negative here, keeping it insulated with the help of an insulator. And now you connect it to the kit. Here, this is the heater output. You will be connecting this to the heater output. And when you use the switch, this is the switch to keep the heater on or off. And this is to control the heat. You want to heat it more or you want to heat it less, you can use this heater control. So that is why we call it as a kit. You have the power supply to allow the current to flow through it. And then you have the ammeter, microammeter to measure the current. And this is the heating arrangement. This is the heater output. When you heat it and keep the switch on, the oil here gets heated up. Okay. And then the semiconductor also gets heated. So as the temperature increases, you will note down the readings here. So this is the arrangement, and this is the thermometer, which is in degree Celsius. We are using a thermometer in the Celsius scale. Okay. So all this is required to do the experiment. Now, the theory behind the experiment. Semiconductors are classified by fully occupied valence band and unoccupied conduction band. Here, I am not talking about the conductors and the insulators. I have given you the broad classification between conductors, semiconductors and insulators. Insulators, the band gap is very high. They do not conduct at all. Conductors, there is an overlap between the valence band and conduction band. So, the electrons can go very easily into the conduction band. They conduct very easily. But when it comes to semiconductors, they are classified by the fully occupied valence band. So, their valence band, if I am talking about this, is the valence band and this is the conduction band, and there is a gap we have seen of the order of around 1 electron volt. So, this is the conduction band. So, if you see these semiconductors, they are classified or they are recognized by the fully occupied valence band. This valence band is fully occupied, means the valence electrons are filling the valence band because that represents the energies of all the valence electrons. Now, according to the band theory, semiconductors act as insulators. They act as insulators at absolute zero. At absolute zero means I say it is 0 Kelvin. How are they acting? They are acting as insulators. Insulators means which do not conduct. Why they do not conduct? Do we have any electrons in the conduction band? We have seen here, the valence band is full and the conduction band is unoccupied. Unoccupied means there are no electrons in the conduction band. Means there are no free electrons. When there are no free electrons, it does not conduct. It cannot conduct. So, they behave as insulators. This is at absolute zero. So, this is one very important point you need to understand. The semiconductors are behaving like insulators at absolute zero. What is the reason? The reason is the empty conduction band, means there are no free electrons in the conduction band. Now, above this temperature means if you go slightly above 0 Kelvin, means I can say even a room temperature of around 20 to 25 degrees Celsius is the room temperature. Okay. So, even at that temperature and still staying below the melting point of the solid. When we are talking about, you need not go to such high temperature where the solid or the semiconductor you are taking itself will melt. Staying below that temperature, the metal would act as a semiconductor. Semi here means it is partially conducting. It starts conducting. The one which is an insulator at absolute zero will now start conducting. Now, the metal would act as a semiconductor, means it will start conducting. How? Because when we are increasing the temperature, I said when we increase the temperature slightly, even at room temperatures, 20 to 25 degrees Celsius, if I convert it to Kelvin, so 20 plus 273. So that will be around 293 degree Kelvin. At this temperature, what happens? If that energy is sufficient for the electrons to go from valence band to conduction band, because there is a gap of 1 electron volt, these electrons will have to overcome this gap to go into the conduction band. So, once they go into the conduction band, what does it represent? They are free electrons. If they are free, they start conducting. So, what is the temperature doing here? When we are increasing the temperature, the electrons are gaining sufficient energy to move from the valence band to the conduction band. Because the band gap is very small, even at lower temperatures, they gain sufficient energies to go to the conduction band and then they start conducting. So, we are calling it as they act as a semiconductor. Now, with the small band gap in between these two bands, it takes certain amount of energy to excite the electrons from valence to conduction band. So, hope you understood this point. What is this excitation of electrons? from valence band to conduction band. What it takes is they require certain amount of energy. Those electrons which are in the valence band, they require certain amount of energy to go from the valence band to the conduction band. So how are we supplying the energy? By increasing the temperature. So here the electrons are moving from the valence band to the conduction band. Now, semiconductors are defined to have conductivity in between an insulator and a conductor. So that is why we are calling them as semiconductor. When I talk in terms of conductivity and not the band gap, I am talking as in terms of conductivity. Their conductivity will lie in between that of an insulator and a conductor. Conductor is highly conducting, insulator is not conducting, but the semiconductor will lie in between that of a conductor and an insulating conductor. And their characteristic conductivity is from their small band gap. I hope it is clear by now how the small band gap plays a role in helping the semiconductor to conduct. Because the band gap is very small, even with the supply of little energy, the electrons are able to jump into the conduction band. They are becoming free and they start conducting. So due to this property, semiconductors are very common in everyday electronics. So whenever you see an electronics equipment, you will find semiconductors. So whether you are an electronics engineer or a computer engineer or a mechanical engineer, wherever you are talking and you are using, even for that matter, if you are using it in your day-to-day life, whatever electronic gadgets you use, you will find semiconductors. They have become a part and parcel of our life now, semiconductors. So what is the property that is helping? Because of their semiconducting nature and because of the small band gap. No? So you must be wondering, when we have conductors which are conducting and we have insulators which do not conduct and which are used to protect the instruments against this conduction of heat or current, why do we have to use a semiconductor? Because they do not short circuit like a conductor. When there is continuous flow of electrons or electrons in the conduction band continuously, it may give rise to short circuit. No? In order to avoid that, so semiconductors are mostly preferred in electronics. Now, having a band gap. No, in conductors, there is no band gap. In insulators, the band gap is huge. Having a band gap prevents short circuit since electrons are not continuously in the conduction band. Where are they? Where are the electrons if they are not in the conduction band? They are in the valence band, and only when you supply a required amount of energy for them to overcome the band gap, then only they are able to go into the conduction band. So this band gap prevents short circuits. They are not continuous. The electrons are not continuously in the conduction band. So a small band gap allows for the solid to have strong enough flow of electrons. Now, you also need to have a strong enough flow of electrons. If the band gap is huge, then it becomes difficult to pump the electrons from the valence band to the conduction band. If it is small, then it becomes easy for us to move the electrons from the valence band to the conduction band. So, this small gap is allowing to have a strong enough flow of electrons from valence to conduction band in order to have some conductivity. So here you understand the importance of the small band gap and how they start conducting because of the small band gap. Now, therefore, semiconductors are widely used in microprocessors, microelectronic components, transistors, rectifiers, amplifiers. All these big terms or big components, whatever we use, are very important in day-to-day life. All these are made up of semiconducting materials. So, semiconductors are widely used in all this. So, their applications are huge. Now, let us come to the formula which we use to calculate the energy gap. So, whenever we are talking about a formula, this formula which we are going to use, Eg is equal to 2 into 2.303 into K. Here, K is the Boltzmann constant. K here is the Boltzmann constant. into slope. So when you are using this formula we are not going to derive in the experiment. This is the one which you learn in the theory, you derive it, and whatever you have learned in the theory, you are applying that formula here and doing the experiment and observing the result, whether it is matching with the theoretical value or not. So Eg is the energy band gap, is represented by Eg. The formula is 2 into 2.303 into K into slope. This is the slope which we get from the graph, which I'll be explaining in the next slide. So K here is the Boltzmann constant. Boltzmann is the name of the scientist. He gave us this constant 1.3806 into 10 power minus 23 joules per Kelvin. This is joules per Kelvin because the temperature we are measuring in Kelvin, degree Kelvin, and the energy we measure in joules. Now, Eg is equal to 2 into 2.303 into 1.38 into 10 power minus 23 means we have substituted the value of K into slope. Okay. So, the energy we will get it in joules. So, energy always measured in joules. As I told you, this is the unit to measure the Boltzmann constant. Now, most of the times when I was talking about the energy gap, I was talking in terms of electron volt. Electron volt. I said the band gap in a semiconductor is of the order of 1 electron volt. So what is 1 electron volt equal to? 1.6 into 10 to the power of minus 19 joules. So you need to know this conversion, 1 electron volt. Suppose I do not want to write the energy gap in terms of joules. I want to write it in terms of electron volts. So I need to divide it now with 1.6 into 10 power minus 19. Then I get the energy gap in terms of electron volt. So Eg will be given by 2 into, if I write it very clearly, it will be 2 into 2.303 into 10 power minus 23. This is the value of K into the slope which we get from the graph divided by 1.6 into 10 power minus 19. So whatever value we get, this will be in electron volt. So that will be the conversion. I told you 1 electron volt is 1.6 into 10 power minus 16. So whatever we are getting in joules, you will divide it with this value so that you will get it in electron volt. Now let us understand the graph. The graph, because the slope from the graph is helping us in calculating the energy gap. So what is the graph you are going to plot here is, this is the origin. I say this is the x-axis. So along the x-axis, you take the values of 1 by T. T here is the temperature. So 1 upon T values you take along the x-axis, and log R to the base 10 you will take along the y-axis. This is the y-axis, positive y-axis. So I say this is y, this is x. So along the x-axis we are taking 1 by T values, and along the y-axis you are taking log R to the base 10. Now you must be wondering, we were only increasing the temperature and noting down the saturation current. How are we going to get the value of R? So we'll use the famous Ohm's law. We have V upon I is a constant. What is Ohm's law? What does Ohm's law say? As long as the physical state of a conductor remains the same, the ratio of the potential to its current is always a constant, which we call it as R. So in this experiment, we have put a constant voltage. When I have shown you the apparatus, I have shown you a constant supply. So constant voltage we are using, which is around 1.5 volt. So you know the voltage, and for different values of current, you calculate the value of R using this formula. R is equal to V upon I. Okay. So suppose my current is say 2 microampere. So my voltage is 1.5 volts upon 2 microampere. So I can convert the value of R. So of course I'll have to convert this microampere into ampere, that is 10 power minus 6, or I can write it as 1.5 into 10 power 6 by 2. So this gives me the value of R. So that is why we are taking log to the base 10 R. Okay. So these values of R, log R values plotted along the y-axis and 1 by t values taken along the x-axis. Then how do you get the slope? So the general formula to get the slope is y2 minus y1 upon x2 minus x1. So what are these x1, x2, y1, y2? Now whenever you plot a graph, you have a graph here. So for different values of 1 by t, you get the values of log R. You will keep plotting the values and you will join them. Here in this, you get a straight line. A straight line when you plot the values of 1 by t along the x-axis and log R along the y-axis. Now when you have, take any 2 points here, I will denote this point. The coordinates of these points are x1, y1. And here I take the coordinates of this point as x2, y2. These are the two coordinates where I am finding the slope of the graph. All those who have done mathematics, you know how to find the slope. So I am talking in terms of coordinates now. x1, y1, x2, y2. So if I try to get the values, so this will be the value of x1 along the x-axis and this will be the value of x2. Because I see many students struggling how to get the slopes. So I want to explain it to you very clearly. So this is the value of y1 and this is the value of y2. So if you know the coordinates, you can draw perpendiculars onto the x-axis, onto the y-axis. So what you get here is, this is x1 and this is x2. This is y1 and this is y2. So now I want to get the slope of this. So it is simply y2 minus y1 upon x2 minus x1. That gives the slope. y2 minus y1 upon x2 minus x1. What is it we are taking along the y-axis here? We are taking log R values to the base 10. So here when we take y2 minus y1, we get delta log R. Delta here always shows the difference. Delta denotes what? The difference between the values of log R. So the difference from this point to this point. So delta log R upon delta 1 by t. Because along the x-axis we have taken 1 by t. So the difference we are getting as delta 1 by t. So you hope you understood. Delta log R will be here log R 10, log R to the base 10, R2 value minus log R1 to the base 10, R1 value. And here I will say 1 by T1, T2 minus 1 by T1. So instead of that, we are representing it by delta. Delta always denotes the fractional change. Okay, change in the values of R2 and R1 here and 1 by T here. Okay, and here T represents the absolute temperature. So you know how to plot the graph. Whatever observations you have noted, you will be plotting the values of 1 by T along the x-axis and log R to the base 10 along the y-axis. You will join all the points, you will get a straight line and then you will have to find the slope of that. So in order to find the slope, you will select 2 points from where you will draw perpendiculars and get the values of x2, x1, y2, y1 and getting y2 minus y1 upon x2 minus x1 gives the slope. And this slope we are going to use in the formula to get the result. Now coming to the circuit diagram. So this in the circuit diagram, first we will start from the diode. I told you this is the symbol for a semiconductor diode. This is the positive side and this is the negative side. When I have shown you the symbol, I have shown you this is the symbol. This is the positive. This is the negative. Now in the aim itself, we have mentioned we are going to study the reverse saturation current. Means, what do you mean by reverse saturation current? You are going to connect the diode in reverse bias. How you are going to connect the diode? You will connect it in reverse bias. What do you understand by reverse bias? I told you this is positive, this is negative. Now, the positive of the semiconductor diode is connected to the negative and the negative is connected to the positive. This is the power supply where this is positive and this is negative. Okay. So here, if I'm talking about this diode, the positive is connected to negative and the negative is connected to positive. That is what we call it as reverse bias. I'll explain it to you at the end while showing you the PN junction diode also. So now, how did we connect the diode? We have connected it in reverse bias to read the reverse saturation current. Now we have kept this after connecting. We are putting it immersed in an oil bath. What is this? This is the oil bath. And of course, we keep a thermometer immersed in this oil bath to note down the temperature. So this will be the thermometer. Now, this is the supply. This is the diode. And you have a microammeter to measure the current. So from the negative, we have connected it to the positive. And from the negative of the power supply, we are connecting it to the microammeter negative. And the positive is connected to the positive of the semiconductor diode. And this is the voltmeter. This is what? Voltmeter. Voltmeter is used to measure the voltage across this two terminals, the power supply. This is used to measure the voltage. This is used to measure the current. Microammeter because it is very small. I hope the whole circuit. This is a very simple circuit where you have a power supply here. This is the power supply. And this is the setup for heating the semiconductor diode. We have seen how we are connecting it in reverse bias. And then to measure, we are using a microammeter and then an voltmeter to measure the voltage across the circuit. Now let us see the procedure. I told you, you should have a plan how you are going to go about the experiment. So we are going to see the stepwise procedure. The diode is connected in reverse bias. So this is the first thing you need to understand. So the diode is connected in reverse bias as shown in the circuit diagram. I have explained it to you in the circuit diagram how we are connecting it in reverse bias. Then the diode is placed in an oil bath. We have taken a container, a copper container, which is a very good conductor. We have filled it with oil and we are keeping the diode immersed in that oil. And I also explained why we are using an oil bath to have uniform heating. The temperature will be uniform throughout the oil. Then the temperature of the oil is noted with the help of a thermometer. So first, before starting the experiment, you need to note down the temperature of the oil. How you are noting it? With the help of a thermometer. Here we are using a thermometer in the Celsius scale. Okay, later on I'll explain how do we convert it into the Kelvin scale. Now, a constant potential difference of 1.5 volt is applied and the current is noted. Now you are going to apply, you are going to connect it to the power supply in the reverse bias and you will note down the current. Okay, the current IS is noted initially before heating. You have just taken the semiconductor, you kept it immersed in an oil bath, connected it to the power supply. You will note down, you will keep a constant potential difference of 1.5 volt and you will also note down the temperature. Now you will switch on the heater, keep the heater on. So when you start heating it, the temperature of the oil keeps on rising, which you can note down with the help of the thermometer. You will observe it with the help of the thermometer. Now, as the temperature of the oil increases, the semiconductor diode that is kept immersed in the oil also gets heated up. So now you heat it to a temperature, say to around 80 degrees Celsius. Okay. And note down the current. After heating it, after you just allow it to keep on increasing, the temperature keeps on increasing and let it go till 80 degrees Celsius and you note down the corresponding current. Now you switch off the heater. You switch off the heater means you will stop heating. When you stop heating, what happens? The temperature gradually decreases. Now it has started increasing when you are heating. So when you stop heating, and because of the loss of heat due to the convection, into the surroundings, the temperature gradually decreases. Note down the readings of the current as the temperature falls in steps of 5 degrees Celsius. We have heated it to 80 degrees Celsius. Now, you note down the readings as the temperature falls for every 5 degree fall in temperature. So, 80, then 75, 70, 65, 60 and so on. So, here you also need to understand why we are noting down the temperature while falling. We are noting down the current while the temperature falls. We can as well note it down while we are heating it, but we do it only while the temperature falls, because when you are heating it, there may be a sudden rise in temperature or the change may not be uniform. It will be very difficult for you to plot the graph when you note down the readings while increasing the temperature. So what we do is, we will heat it to a temperature of say 80 degrees Celsius. You will stop heating. So when you stop heating, the temperature gradually decreases, and while the temperature decreases, for every 5 degree change in temperature, you are now going to note down the current. So up to 40 degrees. So around 10 readings you may note down. Then what you do, you will plot a graph by taking the numerical values of log 10R in the y-axis. I have explained it in the graph, and 1 by t on the y-axis. So along the x-axis, we are taking the values of 1 by t, and along the y-axis, we are taking the values of log 10R. So how you are getting? We have put a constant voltage 1.5 and you are noting down the current. So V upon I will give you the value of R. You take the log to the base 10 R value and then you will take them along the y-axis. Now we get a straight line graph with positive slope. Positive slope means the value of the slope. Whenever you get a graph like this is x-axis and this is a y-axis. This is the graph for which the slope is positive. No? Because y2 minus y1, if I take like this is y2 minus y1 and this is x2 minus x1, will always be positive. So this is a graph with positive slope. So you also sometimes have where the temperature falls. If you are increasing the temperature, if it falls, then what happens? The slope may be negative also. So here we are talking about the positive. We are not talking about this. We are going to talk about the positive slope. Now the slope of the graph is found out and the band gap energy is calculated using the formula. What we have seen, 2 into 2.303 into K into slope. That formula we are going to use to calculate the energy gap. Now, let us see the demo of the experiment. The aim of the experiment is to determine the energy gap of a given semiconductor diode by measuring the reverse saturation current at various temperatures. Let us see the apparatus that is required. A semiconductor diode which will be kept in an oil bath, taken in a copper container and kept enclosed in a wooden box. We have an energy gap semiconductor measurement kit where there is a provision for the fixed power supply, a microammeter to measure the current and an arrangement for heating. This is the switch for keeping the heater on off, and there is a knob to control the heat, and this is the heater output which will be connecting it to the semiconductor diode. Now let us see the circuit diagram. The N type of the semiconductor diode is connected to the positive of the power supply and the negative of the power supply is connected to the microammeter negative. Microammeter positive is connected to the P type. And we also have a voltmeter across it to measure the voltage. Now let us see the circuit connections. the negative, this is the negative, that is the N type of the semiconductor diode, N terminal, and this is the P terminal, positive. So we are connecting the N to the positive of the supply, that is in the reverse bias, and the negative is connected to the negative of the microammeter, and from the positive we connect to the P end of the semiconductor diode. Now we will also connect the heater output to the calorimeter. This is how we connect from the heater output. Now we will keep this thermometer immersed in the soil bath. Note down the temperature before immersing. So it will be at room temperature, say around 30 degrees Celsius. So the room temperature is around 30 degrees. So we keep it immersed, the thermometer, and switch on the apparatus. Switch on this and also keep the heater on. Now we need to focus on the temperature. As the temperature increases, the current also increases. We can note down the values of current from the microammeter. But what we do here is we will heat the semiconductor diode, say to a temperature of 80 degrees Celsius. Till 80 degrees we will heat it and then switch off the heater. Once we switch off the heater, the temperature gradually decreases and we note down the values of current while the temperature decreases. Note down the values of current for different values, say with a difference of 5 degrees Celsius, note down the current and tabulate the readings as required. Hope you understood the demo very clearly. Now let us see how we are going to tabulate the readings. So in order to note down the readings, you should have a very clear observation table. Okay. So what is it we are going to study? We are going to study the variation of in current, the reverse saturation current with temperature. Means as the temperature varies, the reverse saturation current varies. So we are going to note down the values. So what we need here is the temperature first thing. Okay. So the temperature we are noting down in degrees Celsius. Okay. So T degrees Celsius will be the first column in temperature. Then you need to convert this degrees Celsius to Kelvin. Why Kelvin? Because if you see the SI, we are going to do the experiment and all the readings in the SI system. We generally follow the SI system. You know all the fundamental units in the SI system. So the temperature has to be in degree Kelvin. So we need to follow the same system throughout. So what we are going to do here is we are going to convert it to Kelvin. So what is the conversion? That also you need to know. T degrees Celsius will be equal to T plus 273. This will give us in Kelvin. So you will simply add 85 plus 273 will give you 358. This will be Kelvin. So like that, whatever temperatures we have heated it up to say 80 or 85. I have shown you here from 85. So for every 5 degree fall, we are noting down the current I said. So 85, 80, 75, 70. So till we are going till 40 degrees Celsius. So these temperatures which are in degrees Celsius, we are converting them into Kelvin. How we are converting them to Kelvin is using the conversion T plus 273. Okay. Now after that, because we are going to plot a graph for 1 by T versus log R values, we are going to put this also. Then it becomes very simple. That is the advantage of using the tabular column. So how do you get the value of 1 by T? Suppose I have 358. So I'll have to find out the value of 1 upon 358. So I will get the value as 0.00279 around. Okay. So I'm getting 1 by 358. I have to find the value of 1 by T. Now capital T here I am showing it in degree Kelvin. So 1 upon 358, I'll get 0.00279. So for me to plot it on a graph, or for convenience sake, I will write it in the standard notation. I can write it as 2.79 into 10 power minus 3. I can shift this decimal places 1, 2, 3 and put 10 power minus 3. So that is why I'm putting 2.79, and for all the values here I take 1 by 353, 1 by 348. For all the values I'll have 10 power minus 3. So instead of writing for each reading, I have put here 10 power minus 3. No? So some students get confused. You get the value of 1 by t and then multiply it with 10 power minus 3. Okay. Actually, what you have to understand here is, you are finding the value of 1 by t, you get 0.00279. You are representing it as 2.79 into 10 power minus 3. So whatever a value I have here, this should be multiplied by 10 power minus 3. Then only I'll get the value of 1 by t. Then we are noting down the current values. So the current here, we are directly using a microammeter. So whatever reading you get here, you will get it in microammeter. Later on, we will convert it into ampere. Again, because we'll use the standard notation that is in amperes in SI system. So this is the current. So after you get the current, we are using the formula R is equal to V upon I. V is the voltage, the fixed voltage we have seen. V is equal to 1.5 volts upon I is giving us the values of R. Now, again here, because you are plotting for log R to the base 10, you find the logarithm values of R and note down the values. So these are the two columns which we are going to use now to plot the graph, because the major component in the formula which to calculate the energy gap is the slope. Everything depends upon the slope. Otherwise 2 is a constant, 2.303 is a constant, the Boltzmann constant is a constant. But what varies here is the slope of the graph. So as the temperature varies, the values of log R vary. So you have noted down and kept these two columns ready, the values of 1 by t and also the values of log R. Now, how do we do the calculation? So before doing the calculation, we need to calculate the slope. I gave you the formula y2 minus y1 by x2 minus x1, that is delta log R upon delta 1 by t. Now I take the values of y2 as 4.919 and y1 as 4.204, x2 as 3.19 and x1 as 2.79. So how do I get the slope now? Slope is equal to 4.919 minus 4.204 divided by 3.19 minus 2.79. And of course, we should not forget that it has a value of 10 power minus 3 here. Now, all these values, I told you the value of t here, you have 10 power minus 3. So this is 3.19 into 10 power minus 3. 2.79 into 10 power minus 3. So what is the value of slope we get here is 0.715 divided by 0.4 into, I take this 10 power minus 3 up, we get 10 power 3. So this will be 1.785 into 10 power 3 is the slope. So hope you understood how you are getting it from the graph. Y2, Y1, X2, X1, this 10 power minus 3 because 1 upon t values when we are taking, you are getting 3.19 into 10 power minus 3. So you will have to just simplify. You can use your calculator to do these readings. You are allowed to use it in the exam also. So you need to practice using your calculator. So slope is 1.785 into 10 power 3. Now we'll try to calculate the value of Eg. So we have seen the formula Eg is equal to 2 into 2.303 into 1.38 into 10 power minus 23. What is this? 1.38 into 10 power minus 23. This is the value of K, the Boltzmann constant. Okay. And now what is the slope we are getting? 1.785 into 10 power 3 divided by 1.6 into 10 power minus 19. Hope you remember why we are doing this. Why we are dividing it with 1.6 into 10 power minus 19, because we want to express it in electron volt. So when you simplify this, what you get here, the value of Eg as 0.71 electron volt. So this is what you're going to get for Eg. Eg here represents the energy gap. So the energy gap between the valence band and the conduction band in a given semiconductor diode which we are using here is 0.71 electron volt. And I also clearly told you the value of Eg for germanium is 0.71. So whatever semiconductor we are using here is a germanium semiconductor. And for silicon we will get around 1.1 electron volt. So the energy gap of the semiconductor is given by 0.71. So how we are getting, you have taken almost around 10 readings. Okay. So you will take all the readings, you will take the average of all the readings and write the result. You will get the result as 0.71 electron volt. Now coming to the Viva Voice questions. I told you these are oral questions, or which you will have to answer orally using all your communication skills. Okay, which will test your knowledge regarding the concept and also the practical skills which you have acquired. So there will be mostly straightforward questions based on the conceptual questions. First thing, if you have to do the experiment, you should first understand what an energy gap is. So the first question here is define energy gap. So what is an energy gap? It is an energy range in a solid where no electronic states exist. So if the examiner asks you to elaborate it more, then you may have to explain it with the help of the diagrams we have seen in the beginning. Okay. So the gap between the highest level of the valence band and the lowest level of the conduction band, you can draw the energy band diagrams and then explain also. Then the second question is, what are intrinsic and extrinsic semiconductors? Intrinsic semiconductors are pure semiconductors. Extrinsic semiconductors are impure semiconductors. So if you have to answer the question simply, they are pure semiconductors and they are impure semiconductors. Then if you are asked to elaborate what are pure semiconductors, what are impure. If you take a semiconductor, suppose you have taken a silicon crystal. If all the atoms in that semiconductor are only silicon atoms, it is a pure, where there is no impurity at all. Then you call it a pure semiconductor. Then extrinsic means impure. Impure means you will add some other material, some other atom to the pure semiconductor, then it becomes impure. I'll explain it to you very clearly, the classification. In semiconductors, the broad classification, if you see, intrinsic semiconductor and extrinsic. What is intrinsic? Intrinsic is pure semiconductor. Extrinsic means it is impure. Why it is impure? Because we are going to add an impurity. So what are the examples for pure form? You should also know the examples for pure form of semiconductor, germanium and silicon. These are the two examples for an intrinsic semiconductor, which is a pure semiconductor. Now coming to extrinsic semiconductor, I said it is impure. How is it impure? When you are adding a pentavalent impurity, it becomes an N-type semiconductor. When you add a trivalent impurity, it becomes a P-type. All this you will be studying in the theory. Okay. So whatever you have studied in the theory, you are going to recollect here. Okay. So in pentavalent means, penta means 5. Those elements which have 5 valence electrons, if you are adding such type of material, then you will get an N-type semiconductor. The examples we have for pentavalent impurity are phosphorus, arsenic, antimony. All these are examples for pentavalent. Pentavalent means what you have here? 5 valence electrons. Okay. And here we are adding a trivalent. Tri denotes 3. So if you are adding an impurity which has 3 valence electrons, if you are adding an impurity which has 3 valence electrons, then you will call it as a trivalent impurity. Example are gallium, boron, indium, aluminium. All these are trivalent. So when you are adding an impurity, it is becoming impure and then you call it as extrinsic semiconductor. And when you are adding a pentavalent impurity, you call it as donor impurity also. So the examiner may ask you, is N-type a donor impurity or a acceptor impurity? Sorry, this is an acceptor impurity. Okay, donor means why it is called a donor? Because it has 5 valence electrons. Whenever you take a pure semiconductor, it will have 4 valence electrons, silicon or germanium. So 4, when you add 5 here, this is always ready to donate 1 electron. So you always call it a donor impurity. And in acceptor, you are adding 3 valence electron, an impurity which has 3 valence electrons. So it is always ready to accept 1 electron. So you call it as acceptor impurity. Now, if you see in the pure form here, the number of electrons is always equal to the number of holes. You call it as intrinsic concentration. Ne is equal to NH. Okay. I hope this is clear. What are intrinsic? What are extrinsic? Pure, impure, and in impure again you have N-type if you are adding pentavalent impurity. You have a P-type if you are adding a trivalent impurity. We have also seen the examples for pentavalent. And why it is called a donor impurity? Because it is always ready to donate 1 electron because it has 1 excess electron. And here it is always ready to accept because it has 3 valence electrons. Now, if you have to go in depth and understand, I have put a slide which makes it very clear for you. It is in the pure form. It is impure by adding a trivalent impurity or a pentavalent impurity. It will become an extrinsic semiconductor. And here, the number of holes is always equal to the number of electrons because you are not adding any impurity. It is in the pure form. So, the number of holes is always equal to the number of electrons. Here, the number of free holes are more in P-type. If you see P-type, the holes are more. We call them as the majority carriers. And number of free electrons are more in N-type. In N-type, the electrons are more. N-type, we have seen pentavalent. They are ready to donate. They have more electrons. So, the number of free electrons are more in N-type. Now, the Fermi level lies in between the valence and conduction band. This is also a very important concept, Fermi level. Fermi level tells you about the probability of occupancy of electrons in the valence band and conduction band. In other words, I can also tell you that it is the highest occupied energy level in a given band. Then the ratio of majority and minority carriers is unity. If the number of electrons is equal to the number of holes, then Ne upon NH will always be equal to 1. So the ratio of majority and minority. In this case, because they are equal, there is nothing like majority or minority. I will simply consider the number of electrons upon the number of holes. It will be giving us unity. When you see here, in P-type, I say the majority carriers are holes, and in N-type, the majority carriers are electrons. So here, if you take the ratio of majority and minority is not unity. No? In a P-type, because the number of electrons are less than the number of holes, this value will always be less than 1. And if you take an N-type, because the number of, this is for P-type. If you take N-type, because the number of electrons are always more than the number of holes, it will be greater. So it will never be unity. It will be maybe less than, depending upon the type of impurity we have added and depending upon the type of semiconductor it is, you will either have it less than 1 or greater than 1. Now, how is a PN junction formed? So, you need to understand, because whenever we are talking about a semiconductor diode, it is nothing but a PN junction diode. How is it formed? When a layer of P-type semiconducting material is placed with N-type semiconducting material in such a way that the P-type atoms combine with the N-type atoms across the surface of contact. And then you get the p-n junction. Now you know what is a p-type material. When you are adding a trivalent impurity, it becomes p-type. When you are adding a pentavalent impurity, it becomes n-type. So you are bringing a p-type material. Say this is p and this is n. You are bringing this near to an n-type material. Okay. And how you are placing it such that the atoms of the p-type combine with them out of the n-type, and you will have, this is the junction, which you call it as the p-n junction. Okay. Now, how is it formed? You study this very in detail in the theory. There are different methods. I'll just list down the methods which we use to form the p-n junction diode. A grown junction type, where a p-type material is grown on n-type. Or a fused type, where you will fuse them together. Or a diffused junction type. These are the different types which you study in your theory. Okay, how do you get a p-n junction diode? Now, what happens in a p-n junction diode? So, this is the p-type we have seen, and this is the n-type. So, we have seen that in p-type, in the form of the junction, what is happening? You have two separate semiconductors of p-type and n-type are brought together. So, this is the p-type. This is p. And this is n. They are brought together. Now, what does the p-type has? Because it is p-type, I said this is always an acceptor impurity. There are holes. The holes are denoted like this. These are the holes. Okay. So, the p-type will have holes as the majority carriers. All these are holes. These are the majority carriers in p-type. Then in n-type, what you have? You have electrons. We are showing them by dots. All these are electrons. They are the majority carriers in n-type. And then what about the electrons here? They will be the minority carriers. Here, holes will be the minority carriers. And whenever here we talk about hole, a hole is nothing but a deficiency of electron. Whenever we talk here in a p-n junction diode, we are talking about hole means it is always a deficiency of electron. Now we'll see how a depletion layer is formed. What is a depletion layer? No? So we have already seen this picture. In the n region, what we have here? We have the electrons as the majority carriers, and in the p region, we have holes as the majority carriers. We are calling it as acceptor impurity. Here we have the donor impurity. So when they are joined in the region of contact, the free electrons diffuse from n region and combine with the holes in the p region. So this is the point of contact. They are placed in such a way the p inside atoms will combine with the p side. So what is happening? There is diffusion that is happening here. The electrons from the n side will diffuse onto the p side. So when the electron is going from here to here, what is happening is it will leave a positive charge on the n side. You can see these positive charges. Okay. So when the electron has diffused onto this side, you have the positive charge. So this leaves the n region near the boundary positively charged and the p region negatively charged. So when you have the holes coming over here, you will have the negative charge here. So you on this side, okay, because the holes have diffused onto this side, you will be left with the negative charge. Now as a result, what is happening? There is an electric field that appears in a small region on either side of the junction. So here all this is positive. You can see this is negative. So whenever you have the separation of charges like this, there is always a field which we are denoting here. So an electric field appears across the junction in a small region. The width of this region is very small. Okay. But in this region, you will find this field. And this region, we are calling it as depletion region. Why we call it as depletion region? Because it is depleted of the charges. And the thickness of this region is of the order of 6 into 10 power minus 6 centimeters. The width is around 6 into 10 power minus 6. Now, due to the electric field, there is a potential difference that appears around the depletion region. There is a difference in potential, no? Positive is always at a higher potential and negative is always at a lower potential. So, there exists a potential difference which we call it as a contact potential or barrier potential. We also call it as potential barrier. There is a potential barrier across the junction. Why we call it as barrier, you know? Because you have these charges, the positive charges here. So, when these holes want to diffuse more and come on to this side, they will be obstructing. They will form a barrier for further flow of electrons from N side to the P side and holes from P side to the N side. So, we say that there is a barrier that is formed at the junction which we call it as a potential barrier. And this layer, we are calling it as the depletion layer. Now discuss the forward and reverse biasing. We have already seen the reverse biasing in the start of the experiment. So here we are going to see both what is forward bias, what is reverse bias, what is going to happen if you are going to do the biasing. Now, if an external voltage is applied across the depletion layer, you have seen the depletion region now. No? So we have seen there is N-type here. There is P-type here and there is a region of small width that is formed. In this region, there is a difference in potential because of which there is a barrier. Now, when you connect this N to the negative and P to the positive, a voltage Vf is applied across the region such that the positive of the source is connected to the P side. This is the source. We are applying the voltage. This is the external voltage Vf we are applying. How we are applying? The positive of the source is connected to the P side and the negative of the source is connected to the N side. Then the junction is said to be forward biased. So this is what we call as forward bias. This is forward bias. Now what happens here? This voltage Vf appears across the depletion region. When you are connecting it, this is going to appear across this. And Vb acts from N to B, means the potential due to the barrier is acting from N to P and this is acting from P to N. So what happens here? The electrostatic potential barrier is lowered. So by doing forward bias, what we are trying to do here? We are trying to lower the potential barrier. And what is the resultant potential now? Vb minus Vf. Vf is the applied potential, Vb is the barrier potential. So Vb minus Vf. So naturally the potential barrier is lower. So what for the examiner may ask you, why do you do forward biasing? So forward biasing is always done to decrease the potential barrier or to lower the potential barrier. Now what is reverse? So exactly the opposite of what we have seen now. N-type, P-type. There is a potential barrier that is formed here. Now you are going to connect the N to the positive and this to the negative. This is the applied voltage. So if an external, I will not write it as R, we will denote it by RF. So this we will call it as VR, reverse voltage. Okay, VR. If an external voltage VR is applied across the region such that the negative of the source is connected to the P. So here, this is the negative, this is the positive, positive, negative. So negative is connected to P and positive is connected to the N. So this is positive, it is connected to the N. Then it is said to be reverse biased. And since this potential acts along Vb, means here Vb is acting along N to P and here the reverse voltage also acts along N to P. So the resultant will be given by Vb plus Vr. So on application of forward bias, what is happening? The electric field in the transition region reduces and in the reverse bias it increases. Are you able to understand the difference between the forward bias and reverse bias? You have to explain in terms of connection. In reverse bias, how do you connect N to the positive, P to the negative? And by doing this, the width of the potential barrier increases, or you are increasing the potential barrier. Now, if you want to know more about the experiment, you can refer to your lab manual from your CMS login, or you can also refer to this books, Practical Physics by C.L. Arora, and also Practical Physics for Engineering Students by Vijay Kumar and Dr. T. Radhakrishnan. Thank you. See you again with the next experiment.
Like, share and subscribe. Hit the bell icon for more updates.